In today's lab, we're going to do an aldol reaction between a ketone and an aldehyde. Here is our ketone, that is acetophenone, aceto, and phenone. And the base is sodium hydroxide. The base will convert the ketone into enolate, and the enolate will react with the aldehyde. Okay, so here is sodium hydroxide, which will deprotonate a proton from the alpha carbon. The only alpha carbon in this ketone that has protons is this carbon. So sodium hydroxide will take the proton from that carbon. On the other side, this alpha carbon does not have a proton, so you don't have to worry about which one to deprotonate. The product of this reaction is an enolate. It's the benzene and then the CH2 negative charge. That is a nucleophilic carbon of the enolate. The enolate has a more stable resonance structure. If you want, you can draw that as an option. It is the more stable resonance structure where the negative charge is on the oxygen and there is a double bond between the carbon and carbon, right? So let's put a square bracket to tell that these two are resonance structures. Okay, that's an enolate. Our sodium hydroxide is not very strong, so the reaction is not complete, which means a backward reaction is possible, and there may be some ketone unreacted in your flask. You can draw the arrows like this, or if you want, you can erase this arrow and draw the unreacted ketone on the product side. So let's draw this acetophenone. Some of the acetophenone is not reacted. Right. So there are two products. One is our enolate, and this is the unreacted ketone. Now the problem with this is the enolate will start reacting with the ketone because the enolate is a nucleophile, the negative charge is the nucleophile, and the partial positive charge on this alpha carbon could be an electrophile. So there may be some reaction between this enolate and that ketone, nucleophile and electrophile, but we don't want that. To avoid this reaction, what we do is we will introduce the aldehyde in the first step itself. We don't have to wait. So let's add the aldehyde here in the first step. Okay, carbon. This is para-anisaldehyde, which means there is an anisole. Methoxybenzene is also known as anisole. Right, so this is methoxybenzene, anisole, aldehyde. So anisaldehyde, they are para to each other, so it's para-anisaldehyde. This aldehyde is more reactive than ketone. We know that because this partial positive charge is larger than this partial positive charge, and this is more readily available for the reaction than this positive charge. So the reaction will more likely to happen between the enolate and this aldehyde that you added in the first step itself, and which will hinder the undesired reaction. This pi bond will break to make a new lone pair on the oxygen, and the first step also needs a solvent. The solvent we use today is ethanol. Right. Let's draw the product. The product of this aldol reaction is aldol. Okay, here is the benzene, the benzene from the enolate. And the CH2 alpha carbon. And let me draw the new bond using red color. That's a new bond, and the carbonyl carbon, right? Carbonyl carbon, the oxygen with a negative charge, hydrogen on the carbon, and the anisole on the carbon. Okay, so that's the anion, the intermediate of this reaction. Let me put an arrow like that. Now, look at the negative charge here. One way to neutralize the negative charge is protonation. You can add acid. In this case, if you read the procedure, we're adding ice water, that is acid. So this will take a proton from the ice water and becomes alcohol. So I'm going to skip one step. I don't have space in the whiteboard, so I'm going to draw the alcohol here. Right. Now after this, the condensation will occur. Right? The condensation will be initiated by the excess of sodium hydroxide that you added. The NaOH will deprotonate the hydrogen from here, the alpha carbon hydrogen. This is carbonyl alpha carbon hydrogen, and then this will make a pi bond. The hydroxide will be gone. Right? Having excess of sodium hydroxide will push the reaction to go for condensation. So this is not an aldol reaction, this is aldol condensation. You'll have a double bond here and the hydroxide will be gone. Let me draw the product. CH, double bond, hydrogen, there's hydrogen, that is the product, aldol condensation. Take the weight of a 10 ml Erlenmeyer flask, that is our reaction flask. Note down this weight for your calculation. Now I'm going to add 0.26 ml of para-anisaldehyde, that is our electrophile in the aldol reaction. Okay, here's 0.26. Now note down this weight. When you subtract the weight of empty flask and this weight, you'll get the weight of 0.26 ml para-anisaldehyde. Put a still bar. This is 0.25 ml. I'm going to add 0.25 ml of acetophenone. Okay, now we have our aldehyde and ketone. Now we need the base. Here's the base, which is 15 molar sodium hydroxide. Before we add the base, let's mix these two reactants and the solvent. The solvent is 95% ethanol. We need 1.6 ml of that. Here is 0.8. Point 8. .6. So now we have 1.6 ml of 95% ethanol. Let's mix these reactants and the solvent thoroughly before we add the base. Okay, we mixed that thoroughly. Now I'm going to add the base. Okay, let's stir this reaction mixture at room temperature until it solidifies. You can see that the reaction is turning into an yellow precipitate. After letting the reaction to go for a few minutes, I can see an yellow precipitate. I'm going to add 6 ml of ice water. Approximately 6 ml. Okay, that should be 5 to 6 ml, and I can see the white or yellow precipitate. I think that should be our product, and we can go for the vacuum filtration now. Transfer your product. To recrystallize the crude product, let's transfer this into the boiling ethanol. When the crude product is dissolved in the boiling ethanol, let's take the heat off, cool it down to room temperature, and put in the ice bath. Okay, here is the pure product, the Aldol condensation product, and that is the weight of the pure product. And here's the appearance of the pure product.